I've got an early question, Pavel. So you're going to be talking about privacy in relation to the entangled rollup, but is this also going to be applicable to all applications that utilize ZK MIPS? Or is this stuff only going to be applicable to the entangled rollup application? For example, another well-known use case of ours is the hybrid rollup. Are we potentially able to offer privacy to optimistic rollups that adopt ZK MIPS? I mean, like, i.e., is this going to be broadly applicable to many use cases, or is this specifically entangled rollup oriented?
So there's different methods. So there's no one answer for everything. But if they want to, let's say, adopt liquidity optimized um, layer two, or like the universal L2, but that could be called, different names. But the universal L2, there would have to be a module added within that L2, which would enable them to uh, share or unify liquidity across all added L2s. So, this might be like a good way to just share my screen uh, and my drawing skills as well. So if we take a look over here, we can basically see that, if we have like an um, over here, we have a OP rollup, and that could be like Optimism, Arbitrum, Metis, and then there's like, a ZK rollup. And then over here, we have like these two structures right here where as long as they're adopted within the um, universal L2 model, they can still share liquidity across these different ecosystems, share native liquidity. Um, that being said, you can use this as general message passing as well. So if you have like, let's say, an L1 like Ethereum, and then you have another L1 like Avalanche, and let's say you don't want to use like the shared liquidity, you can still interact with these different L1s to L1s without the need to use L2s, as this means. So hopefully that gives a little bit of a clearer picture so that you don't have to use a single structure. It's very adaptable. What we're trying to explain, or what I'm trying to explain here, is that you can use these types of structures to essentially create many different um, unique implementations, which might be more fitting for what you're trying to do. And what you're trying to do, in essence, is to send messages across different ecosystems in a trustless and secure way, with settlement across these different networks without utilizing, let's say, a blockchain in between. So typically, how a lot of bridges work is that it doesn't communicate directly from L1 to L1. We do that, but a lot of other blockchains or other bridges actually use a separate, um, essentially like a bridge. Yeah, I can't spell, but bridge, and then they interact with this bridge, and then this bridge sends uh, relays a transaction to that other L1. But it is up to that bridge to facilitate that transfer. And so the same thing when I'm interacting with this other L1, I send it to the bridge, which then relays it to the other L1. But here is the single point of failure. If, let's say, this bridge network goes down, um, your funds are stuck. So it's not trustless. And there's no way to guarantee that a bridge is secure up until it's too late and they withdraw all your funds. So I'd rather have a mechanic where I am guaranteed that this is secured at least through a mechanism like ZK proofs. And then in this way, I'm able to make these withdrawals. By the way, optimistic and ZK rollups, so how they work is that they use Ethereum's or whatever L1's native consensus in order to validate transactions. So L1 as the settlement layer is used as terminology. Whenever I send a batch from an optimistic rollup to an L1 such as Ethereum, I'm essentially using Ethereum as a settlement layer, which then settles these transactions, which basically means that these transactions that are on Optimism are secured, or on Arbitrum or on Metis, they're secured by the L1 on Ethereum, and we can, with high amount of certainty, say that Ethereum is decentralized enough. There's a lot of node operators. There's a lot of people that are staked within the system. So we can likely guarantee that Ethereum will not be compromised by, let's say, a 33% attack or 51% attack or something like that. But we cannot have the same guarantees with, the example of this bridge right here in between, or like the network that sits in between these two ecosystems. So we cannot have the same guarantees as this over here. So hopefully that makes a little bit more sense. But if it doesn't, definitely we're going to have like way more of these workshops and alongside with the overall presentation of what we are doing here. So let's actually go into, so let me just slowly change my windows over here. All right, can you see this screen? The ZK bridge for privacy. Perfect. Can you see this slideshow? Or is it like this full screen? Okay, so it's a bit zoomed in. Okay. In that case, I'll just keep it like this. Okay. So you guys can see this screen. Okay, perfect. Actually, because I'm using OBS, I don't know how OBS would record full screen, so I can just do it like this and go from slide to slide to slide. It's not, I don't add cool animations to my presentations, but I did before, but now it's a little bit too time consuming. All right, who I am, why you should listen to me. Of course, take everything with a grain of salt, do your own research, but I took a look at different types of structures, processes, environments. So I worked for the Metis ecosystem for 3 years, for the integrations lead for the Metis ecosystem to DevRel lead for ZKM. I'm focused more on like the research and communicating these different ideas. So hopefully other people can take them and apply them to other systems. And then I also built a smart contract platform based on like programmatic influencer marketing called Chorus. So built that from, well, I wouldn't say from the ground up, but enough to know that about smart contracts and how they work, how they integrate. I integrated like abstraction, so wallet abstraction, so that gas fees don't have to be paid by users. So these are very similar mechanics that like other bridges like Connects are using. Connects, I don't know how to pronounce that, but which have gained like huge amounts of popularity. But basically, like simplifying this onboarding process for new users is a very important thing for bridges. Next is that I created the governance framework that's still used by Metis today, and basically following a set of processes and improvements can make all the difference to how a protocol or project operates. So let's just dive in really quick into what ZKM is. I believe I gave a presentation just last week that explained this, but it's such a abstract term that I do want to go in it a bit in depth again. So first of all, I talk about settlement. What is settlement? Settlement is finalizing a transaction where the transaction is not able to be reverted. So what does this mean? Here is a page for Kraken, their support page. Essentially, this says how many confirmations are needed before a chain is finalized. So there's different chains that exist in the ecosystem, and as a result, Kraken has, for their own purposes, because they don't want to give people money in the case of that the transaction doesn't actually resolve, they've set their own parameters for confirmations. So for some, like Ethereum proof of work, since there's not a lot of miners, since there's not a lot of people participating in the network, they need 20,000 confirmations, which take multiple days to settle. And same thing with Arbitrum 1, Arbitrum Nova, you have 14 minutes, 25 minutes for these different types of systems. And so we can say finality can be attained, or at least according to Kraken, finality can be attained within this period of time for these blockchains. At least that's what they're willing to give you money for, based on the amount of time that you spend with the minimum risk that this transaction will be reverted. There can never be a complete 100% guarantee for finality because this is how these blockchain systems work. But you can wait a certain amount of time where it just becomes so unlikely that you would say, okay, we'll resolve it. But as you can see, every network has different finality depending on which network you're using. So what is universal settlement? It means that any computation can be executed by one blockchain, and the results of the execution can be resolved to any other blockchain. So going back to the previous example, we post this, and then this amount of transactions get resolved, and then as a result, I can finalize it on one blockchain, and then send it to another blockchain with the guarantees that these transactions will not be reverted. So universal settlement means that I can essentially specify parameters that the transaction that I post on one blockchain can be resolved to another blockchain. Same in part to how this works. That if I wait 3 to 4 days on Ethereum proof of work, I can be guaranteed that this transaction is finalized, and then send this confirmed transaction to Polygon, which then would enact certain operations. So that's how our mechanism of universal settlement works. How do we do this? Well, we do this through the entangled rollup. And all an entangled rollup is just message passing from one chain to the other using zero knowledge proofs. So here's I would say, a complicated diagram outlining how this all works. But the idea is we can do operations from the rollup contract, and then, so from the shadow contract, we can send transactions to the shadow contract, which then would be replayed on a different chain, and it could be executed, and any form of operation can be executed on the other chain. And that's just the lessons that we're doing today, is just exploring how this system can work for basically any form of anything from privacy to liquidity optimization to governance to reputation. So there's many different types of use cases for this, and I'll outline this throughout all of these types of presentations. Now let's talk about quantum entanglement. Complicated topic, but according to Merriam-Webster, which is a dictionary, a property set of subatomic particles, blah, 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 where one particle is directly and immediately correlated with the equivalent characteristic of the others, regardless of separation in space. So what does that mean? That means this. But then if we look at a quantum network, which does not have a definition, but we are coining, ZKM is building the quantum network. But essentially, if we take these keywords from particle to message, from characteristic to properties, and from space to blockchains, then these definitions are very, very similar. Is that all we're doing is relaying a message that has specific properties to blockchains. And it doesn't matter how separated those blockchains are, whether the separation is in finality, so how it takes like a certain amount of days or a certain amount of hours, or the finalization, or the it is in incompatibility of these different types of virtual machines, right? Ethereum is an EVM. Avalanche is an EVM blockchain. Solana is an SVM, so using Solana VM. Move VM is Aptos, Sui, Movement. They're all different VMs. They're all different blockchains that have their own specific languages. Some use Rust, some use Solidity. What we're doing is we are uniting these incompatible blockchains using a common medium of ZK proofs. So what is ZKM? ZKM is building the quantum network using entangled rollups to enable universal settlement. All right, from there, we have this image, and hopefully this also answers your question, Ben, on this is the overall goal, but it isn't the, I would say, the only way to think about this. We are transferring assets using layer 2s because layer 2s are more cost effective and they can process much more transactions much more efficiently. But the same can be also done from layer 1s, right? Let's say I don't want to use a layer 2. I can still implement this in part and transfer messages via layer 1s. But the reason why we're using layer 2s, because the cost effectiveness and the scalability. Now, a scenario. We're talking about privacy here. So if people saw the previous presentation, we initially talked about how Alice was transferring 100 USDT from Ethereum to Avalanche. And we didn't include privacy in this one. We are including this in this example. So Alice wants to make sure that that people don't know that she even sent funds to a different address. She wants to be guaranteed that this system is trustless. She wants to be guaranteed that the system is extensible so that it can be used within multiple ecosystems. She also wants to know that her funds that she transfers can actually be withdrawn on these different networks. A bridge is essentially transferring one asset from one location, from one blockchain to another blockchain. There's many different types of implementations of bridges. There's like the mint burn bridge. There's the lock and unlock type of bridge. There's with like a variety of other, there's optimistic bridges. ZK bridges are very sparse. Currently, we're on the bleeding edge of all of this technology, but the idea is we want to solve the hard problems first. So ZK is the end game. So why not solve the bridge problem with this? So there's many different types of ways to bridge assets, but this is just a simplified view of what a bridge is. Since I talked about the different types of bridges last presentation, you can go and review that. Probably a video has been posted. But in this case, there's 3 types of bridges: externally verified, natively verified, locally verified. And this was also done by the Connects team, essentially categorizing these different types of bridges. But what we can basically summarize from these bridges is that externally verified, those are not trustless bridges. They're verified by another blockchain in between those two blockchains, which means that the security and the trustlessness of these types of systems cannot be, or you're reducing or increasing your risk to those systems. Natively verified bridges are not extensible. So think of layer 1 to layer 2, or layer 2 to layer 1. I cannot, from those systems, transfer to Solana, because Solana is completely incompatible with, Solana cannot be a layer 2 on Ethereum because Solana has its own system of consensus. So it's not extensible. I cannot use the same systems that I'm using for transferring assets from Ethereum to Optimism, or Ethereum to Arbitrum, or Ethereum to Metis. I cannot use that same system to transfer Ethereum to Solana. Locally verified, such as IBC, these systems are trustless. They are extensible, when integrated. Unfortunately, they're not liquidity optimized. So what this means is that the liquidity optimization means that if I transfer assets using IBC, I don't have a way to, because anybody can plug in any type of network within there, it's very fragmented. And I can't guarantee that, this $100 of USDT will be available on all the networks. And as a user, if I'm coming into this system and I can't transfer 100 USDT because the route isn't there, then that's a very big, impactful user experience that I'm like, oh, well, if I can't do the thing that I wanted to, why even use it? So what are zero-knowledge proofs? Zero-knowledge proofs can be built for two main use cases: privacy and verifiable computation. And we'll explore a way where we can do both in this method, but specifically focusing on privacy. So how a scalability ZK rollup works: we take a batch of transactions, generate a proof, and send the proof to layer 1. How a privacy ZK rollup works is that essentially it's locally generated by you, the user. And I'll draw this out so that we're not just listening to my words, but you locally generate the ZK proof on your computer, and then with private data. Nobody else knows this data except you. But in making the ZK proof, you essentially prove that all of the data that was inputted into this computation was correct. So if I say that I need to input two numbers and the only requirement is that they're positive, if I input a negative number, then the proof will fail. If I input two positive numbers, then the proof will pass. So these are the types of operations and parameters. We don't know what those two numbers are. We just know that they're positive. So this is how essentially a privacy ZK proof generation process works. And yeah, we're essentially using entangled rollups to facilitate these messages within this private L2 system. So now let's take a look into this. So I've talked a little bit about just the general, what we are, what we're working towards, what the scenario is of Alice wanting to transfer 100 USDT from Ethereum to Avalanche. So now let's look at the private universal L2. There is an EIP 7503, zero knowledge wormholes private proof of burn. In there, we have the description where people can burn their assets by sending it to an unspendable address, and later build a ZK proof showing that some amount of tokens reside in an account that are unspendable, without revealing the account. So this is a really cool way to essentially secretly burn assets. I guess let me actually go into the going to change my windows and going to go into this guy. So just to give like a live visual of what I mean for this system. Initially, we talked about sending assets to a burn address. So a burn address is like 0x dead, 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 etc., etc. So this is an obvious burn address. It just, or 0x0000 dot dot dot, right? So both of these are essentially labeled. If you type these addresses in to Etherscan or wherever, they are used as public burn addresses, essentially as a way to say to people that these assets are no longer in circulation. So because these assets are no longer in circulation, I'm able to essentially, you provably reduce supply in this way. Now, what if there was a way that I could essentially send it to an address that's looks like a real address, 0x A1B 3 4 3, etc., etc., etc. So this looks like a legitimate address. But in this EIP, they mention how they can generate a regular looking address without disclosing to people that it's actually an unspendable address. Nobody knows the private key. So as a result, because nobody knows the private key, it's unspendable. It's the same thing as sending assets to one of these guys. So with looking at these types of systems, when we're trying to burn assets, traditionally we use these two, or another one that could also signify that nobody owns the private key. But in this case, we can secretly burn assets by sending it to what looks like a regular address. So this is what this EIP essentially is stating. And then they basically go on and say that we can use this as a means for people to burn their ETH and then mint it on the Ethereum network. Now, of course, the use case for this is only like privacy within the Ethereum ecosystem. But what we're using this and what we're developing, or people, of course, like in the future, can take a look at, is we can then take the public address, send however much, like 100 USDT to it, and as a result, these assets are no longer in circulation. After we send 100 USDT to this address, we can then generate a ZK proof from this interaction. So I've sent 100 USDT. I then would be able to generate a ZK proof that I have sent 100 USDT to this address, which, along with this ZK proof that I generate, I have another ZK proof that basically says that this address right here is unspendable. So I generated a ZK proof, ZK proof some time ago. So, and then I can include this within this other ZK proof. So I can include ZK proofs inside of other ZK proofs, and essentially have a way that as input parameters to this guy, this ZK proof proves that this address is unspendable. This ZK proof proves that I've burned this amount of USDT. I know it's looking a bit messy, but let me just undo a little bit of this. So hopefully that makes sense. Is that I initially, so step one, generate a ZK proof that this address is unspendable. So that's step one. Step two is that I send 100 USDT to this address. So then send. Step three is that I generate another ZK proof saying that I have burned 100 USDT, or sorry, yeah, 100 USDT, and as input parameters, I basically say that this proof is provided within this proof. So hopefully that makes sense to the three-step process for generating a ZK proof that essentially proves that I transferred assets to a burn address, which is not publicly listed as a burn address. All right, so going back to the slides, change windows, back to these slides. Okay, so, all right. This is I would say like a better visually appealing diagram for this. We have me depositing, or Alice, sorry. So this is Alice wanting to transfer $100 USDT from Ethereum to Avalanche. So we would deposit 100 USDT initially. We would then burn to the burn address. Remember, the burn address is not public in the sense that 0x0000 or 0x dead is public, but we are generating a ZK proof to prove that the assets that we're sending are unspendable. After that, after proving that the address that we generated is unspendable, we then generate another proof, or we send the 100 USDT to that address. We would then generate another proof to then have a ZK proof saying that we have burned 100 USDT. Another important property is that we don't need to know where we burned those assets. So technically speaking, this proof we can remove. So if I were to do this, we can essentially all Avalanche would see is just this. We have a proof in which we can redeem 100 USDT on the Avalanche layer 2. That's all we have. We just know where the destination of the assets that are to be minted. We don't care where those assets existed. We don't care where those assets were burned. As long as they're part of this universal L2, we don't care. All we care is that this proof is valid. If this proof is valid, then that means I as Alice, or Alice as Alice, is able to mint this amount of USDT on the Avalanche Universal L2. That's all it's saying. I don't need to know where the assets came from. I don't need to know that it came from Ethereum. I don't need to know that it came from Solana. I don't need to know that it came from movements or wherever else. All I know is that $100 was removed from circulation in some chain, and as a result, I can mint a corresponding amount of assets without increasing the supply. So hopefully that made a bit of sense in terms of how this mechanic works. So the summary. First, it's private. We do not know where the origination of the funds are. We don't know which address those funds are that we're using to burn. So in going back to the previous example, where we essentially burned it to an address that was 0xA1B343, etc. Nobody knows that that is a burn address. Only we do, and because we have the ZK proof that proves that it's a burn address. The proof that we generate, the second proof, the proof that we're using to redeem 100 USDT, this does not show which chain we burned it on. So what the proof shows is that we have removed 100 USDT from circulation in a chain that's connected to the universal L2. We don't know which chain. We don't know who did it. We just know that those assets were taken out of circulation from whatever type of blockchain. Finally, when the ZK proof is redeemed, the user, so Alice, would input the redeem address to the destination L2. Remember how you can, if I could take this proof that I generated, let's say to claim 100 USDT on Avalanche, I can only claim it once. And if I claim it once, then that means that I cannot claim it again. That's called a double spend or double redeem or whatever you want to say. But this is very important. The user inputs the redeem address to the destination L2. So you can technically generate this ZK proof on behalf of yourself. Now remember, if you expose this ZK proof to anyone else, if you reveal this ZK proof to anyone else, anybody else can claim your 100 USDT because they can just send it to their own address or something like that. So this is the ZK proof that you generated needs to be private. It needs to be generated locally on your computer. And you cannot use, for example, a relay network. So in here, actually, like let me just go a little bit up here. What do I mean by a relay network? Well, over here we have ZKM relayers. So in a fully public system, you would essentially, you don't care that data is public. You just want to send it. The provers generate the proof. The relayers relay the information to the destination. So in this case, because it's fully private, you cannot have anyone else do this for you. Only you can generate the proofs. And this is where we mean ZK for privacy. Although the entangled rollup architecture includes the ZKM relayers and the ZKM provers and the ZKM sequencers, you don't have to use this exact system. And this is what we mean by that we're trustless. This is what we mean by that we're decentralized, is because it's just the proofs that need to be inputted on this layer 1 or on this layer 2 or layer 1, whichever you're sending the assets to. Because, so just if you're going to take anything out of this, when generating private transactions, you have to generate them locally on your machine. When generating, let's say, public transfers for day-to-day transactions, you don't have to run your own prover. So this is very extensible. You can run your own prover. So don't get me wrong, if you're running public transactions, you can run your own self-hosted prover. But just like how many people don't run their own Ethereum node in order to use the Ethereum network, they just use MetaMask or Infura. Consensus created their company, and they have the two companies that they're using. So MetaMask is using Infura for their RPC provider. You can choose to run your own node locally, but you don't have to. So in this case, when you're dealing with public information, you don't have to use it. But when you're dealing with private transactions, you do have to. All right, so
Pavel,
let's go
could I just
down
ask
here. And finally, the
sorry, could I ask a
quality.
question
Yeah,
just on this point?
yeah, of course.
Won't hardware limitations make this infeasible for most users? So if they have to generate their own proofs, um, won't this essentially kind of like mean that users will have to have beefy machines to be able to use privacy functions?
So that's where the arms race between like hardware and efficiency for the actual proof generation process comes from. So, for example, mobile phones. Before, you weren't able to run anything with over, I don't know, a few kilobytes of RAM, and even computers, large computers. Now, you have mobile phones that can run, I don't know, Fortnite, or uh, of course, they have to be optimized for running on a mobile phone. But the idea is that technology is progressing in a way where proof generation will be more efficient, and hardware will be beefier. And we're already seeing this with, for example, the MacBooks have their, M1, M2, M3, which are more energy efficient as well as more powerful than a comparable Intel based chip. So with mobile phones, we can see the same type of progress, and with just generic computers as well. So to that question, I would say like in time, everyone can have this on by default. Everyone can have privacy by default, um, because of the both the hardware optimizations and software optimizations, or hardware, performance increases. But yeah.
Okay, yeah, that answers absolutely perfectly. So, yeah, bearing in mind that this is predominantly for future use, and yeah, as hardware requirements develop inevitably in the coming years, this will become more of a feasible use case, mass adoption, basically.
Mhm. And all the qualities that Alice was looking for, trustless, extensible, liquidity optimized, are all present within this system of a private universal L2. So if you're interested in learning more about this, if you're interested in diving a bit deeper, this EIP 7503 is a great reference to use. Um, and this can be implemented, um, again, across any L2 that's connected within the system. So eventually, um, going to this. So all of these universal L2s can be adapted to without any code or infrastructure changes. Major code, maybe there's some like minor things, but nothing that is a deal breaker for most of these. Um, Privacy can be enabled by default, even if we just start with the public message passing. So if we start with public message passing first, private message passing can be added, um, within this architecture, essentially making everything seamless and connected. Okay. I think that's all I wanted to go into. Um, are there any questions before we end? I guess on 10 or or whatever time zone, like in
There
nine
haven't
minutes, I
actually
would
been
say.
any questions, but I do have a question. We touched on this briefly, I think last Thursday, after Lucas's presentation. But what are like the implications here for regulation? We could does this way of kind of enabling privacy functions is this gonna will there be problems with regulation basically in association with this?
Hmm. It is up. So there can be these, let's say, regulatory modules included, and likely that will be, in order for this to be used, um, these modules will have to be in place. So modules um, that the user can reveal, like reveal keys, they call it. Many different privacy protocols have introduced these concepts. So of reveal keys. Alio, for example, has reveal keys. Um, Railgun has reveal keys. I believe Zcash has reveal keys as well. So it's essentially that you can show that the assets belong to you, and um, in this case, that the assets were not, um, let's say, combined with other, let's say, malicious actors for intent. So um, in this case, how that will be implemented, I guess that would be out of scope for what this presentation shows. It just shows that this mechanic is possible and that it's private. That the only person that will see that you've gotten the withdrawal is on the chain that you made with no association. And again, like this the perfect example, no association to the other chains. So it's kind of like they know that you did it, but they don't know where you did it.
Mhm. Yeah, that's the only question. Yeah, I guess it's like in terms of auditing and like accounting. I guess many people see privacy functions in a
Mhm.
blockchain context as kind of like shady, enabling criminal activity. And I think you said on Thursday that there are ways to do this where it's fully auditable. Um, so yeah, you essentially yeah, all of this has to be done in like a regulatory manner. I can't remember exactly what you said, but you answered it really well on Thursday.
Yeah, yeah. Like I think it's like just the reveal keys or using those, those tools specifically for regulatory purposes, because everyone needs to pay taxes, everyone needs to um, make sure that comply with AML as well. Like we've already have financial systems ingrained in this, and yeah, with this type of system, definitely there could be um, ways that the these types of systems can be implemented, but I am I'm it's out of scope for this presentation. Maybe if someone wants to take a look at it and see how they can implement this um, in a way where the mm, in a way where it can be fully compliant as well, that would be interesting. But again, other privacy protocols exist that have baked this into their software without um, fully compromising on the privacy that they offer. Essentially, it's selective privacy, where I'm able to generate a reveal key and send it to, for example, an exchange or a authority to basically say that no, I'm not involved in any of these like money laundering allegations. So there's there's those things.
Hmm. Yeah, that answers really well. Yeah, thanks very much.
Perfect. I guess that is it for today. We'll probably have well, not probably, we will have a AMA on a Twitter Spaces on Thursday. So if you have any questions that you want answered, or if you have any questions that you want answered, or just need time to think and process, you'll have days, and we'll post the recording of this um, on Wednesday, so that other people have the opportunity to view.
Hmm. Okay, awesome. So yeah, I guess that's it. There's no more questions coming in. Arnie did have a question, but I think it relates more to the subject Lucas was talking about on Thursday. So maybe Barney can save that for Lucas's next presentation, which I'm sure will be, I would say, in a couple of weeks, 2 or 3 weeks max, and we'll see Lucas again doing this. So yeah, awesome presentation, Pavel, and yeah, thanks for answering my questions at least.
Awesome. Sounds good. Thank you all for coming, and yeah, hope to see you in either next week or later this week.